Close your eyes and listen to the clock. It is a steady sound, a rhythmic anchor in the quiet of the room. Tick, tock, tick, tock. It is the sound of time moving forward in a single straight line. It is the sound of certainty. In the darkness behind your eyelids, you can visualize it. Perhaps it is an old analog clock on a kitchen wall, its second hand sweeping past the numbers with mechanical precision. Perhaps it is the digital pulse of a bedside alarm, counting away the moments of the night. Or perhaps it is the great, silent clock of the city outside your window, the traffic lights changing from red to green, the moon arcing slowly across the sky, the predictable rotation of the earth beneath your bed. The sound is patient. It does not hurry. It does not slow down. Each tick follows the last with absolute reliability. This is the first thing we learn about time as children, that it moves at a constant pace, that it never stops, that it carries us all together from past to future like passengers on a train. The clock in your grandmother's hallway, the clock in the courthouse square downtown, the clock on your computer screen. They are all singing the same song, keeping the same beat. If you focus on that sound right now, you can almost feel the mechanism behind it. The gears turning, the spring unwinding, the quartz crystal vibrating precisely 32,768 times per second, dividing itself down to that single audible tick. Humanity has spent centuries perfecting this measurement. We have built our entire civilization around synchronized clocks. We meet at appointed hours. We catch trains at scheduled times. We watch the ball drop at midnight on New Year's Eve, all of us counting down together. 10, 9, 8. The clock tells us where we are in the day. Morning light or evening shadow. Time for breakfast or time for bed. It organizes our lives into blocks. Work time, rest time, the commute between them. Without the clock, we would drift in a formless present, untethered. The clock gives us structure. It gives us deadlines and appointments. It gives us history, a way to say this happened before that. It gives us narrative. Whatever clock you imagine, it has a quality we rarely question. It measures something we call now, this moment, this single shared moment. The clock on your wall and the clock in a kitchen in Tokyo and the clock on a ship in the Atlantic, they are all measuring the same river of time, we assume. They are synchronized swimmers in a cosmic ballet, all moving to the same beat. When it is 3 a.m. here, it is 3 a.m. here for everyone in this time zone. The now we share feels universal, absolute. If someone asks you, what time is it? You can give a definitive answer. The universe, we believe, has a master clock. God's wristwatch, perhaps, or the fundamental ticking of reality itself. Einstein complicated this idea. He showed that time can stretch and compress depending on speed and gravity, but even Einstein's clocks still tick. They just tick at different rates. The assumption remains. There is one timeline, one river of moments flowing from the Big Bang toward the far future. Listen to the rhythm again. Tick, tock. Each tick erases a possibility. Each tock confirms a choice. The second that just passed is gone. It has crystallized into history. The second approaching is potential waiting to become real. This is the architecture of our everyday experience. One timeline, one story, one universe unfolding like a scroll being read aloud. Think about how often you check the clock during your day. When you wake to see if you've overslept. When you're working to see if it's time for lunch. When you're waiting for someone, watching the minutes drag by. The clock is a referee. It marks beginnings and endings. Time's up, we say. Once upon a time, we begin stories. We divide our lives into befores and afters. Before I met you, after I moved to the city, before the accident, after the diagnosis. The clock is the spine that holds the book of our life together. We are born with an intuition about this clock. We believe, deeply and without needing to be taught, that there is only one clock. We believe that there is one now. We believe that when a second passes for you, it passes for everyone, everywhere. We assume that reality is a single, thick book, and we are all on the same page, reading the same sentence, moving to the next word together. Babies do not understand clocks yet, but they understand the rhythm of day and night. They learn that morning brings light and evening brings darkness. They learn that after the bottle comes the nap. After the nap comes playtime, cause and effect, a sequence, one thing leading to another in a straight line. This is how memory forms. This is how we build a self. I remember yesterday. I will do something tomorrow. The thread that connects these moments is time, and we assume it is a single thread, unbroken, universal. This intuition is woven into our language. We say time marches on. We say the past is behind us. We speak of history as if it were a road already traveled, solid and unchanging. We speak of the future as if it were a mist that will clear to reveal a single path. This is the grammar of common sense. It is the foundation upon which we build our identities, our memories, our plans. Every language has tenses, past, present, future, because every culture recognizes this flow. The ancient Egyptians built sundials. The Mayans carved intricate calendars into stone. Medieval monks rang bells to mark the hours of prayer. The Industrial Revolution demanded factory whistles to synchronize workers. Time is not just a concept. It is the framework of society. Without a shared now, we could not coordinate. Without a shared past, we could not learn from history. Without a shared future, we could not plan, hope, or dream. When you woke up this morning, you assumed you were waking into the same world you fell asleep in. The walls were in the same place. The laws of physics were the same. Gravity still pulled down. Light still traveled fast. You assumed continuity. You assumed a thread connecting yesterday's you to today's you to tomorrow's you. This thread is the story of the single timeline. You did not wake up wondering if the sun would rise in the west today. You did not question whether water would still flow downhill. You trusted, with absolute confidence, that the universe operates by consistent rules. This trust is so deep that we call it common sense. We mock those who question it. What goes up must come down, we say, as if it were not just a law of physics but a law of logic itself. The regularity of the universe feels like a promise. The clock's steady ticking is the heartbeat of that promise. And yet, if you think carefully, you realize that this promise is based on memory. You remember the sun rising yesterday, so you expect it to rise tomorrow. You remember that dropped objects fall, so you trust they will fall again. But memory is a story we tell ourselves. And stories, as we will see, are one way of organizing reality, but not the only way. This feeling is safety. It tells you that when you made a choice today, when you chose coffee over tea, or when you turned left instead of right, the other option vanished. It became a ghost, a what if, a memory of something that never happened. In this intuition, the universe is a singular road. We travel down it, and the road behind us is paved in stone, unchangeable, while the road ahead is a fog clearing into a single path. Think about the choices you didn't make today, the conversations you didn't have, the different route you didn't take to work. Where did those possibilities go? In the everyday view, they simply evaporated. They were never real to begin with. They were shadows that disappeared when the light of your decision turned on. Only one outcome survives. Only one branch of the tree gets to be called real. When you chose coffee this morning, the tea-drinking version of you disappeared. When you turned left, the right-turning version evaporated like morning mist. This is a merciful view in a way. It means you only have to live one life. You only have to be responsible for one set of choices. The weight of regret is heavy enough without imagining that every path not taken still exists somewhere, being lived by another you who made a different choice. This is the doctrine of the singular. It is comfortable. It is manageable. It allows us to tell coherent stories about our lives. I did this, then that happened, and so I became who I am. Cause and effect in a straight line. A narrative with a beginning, middle, and eventually an end. It is the story we tell children. It is the story we tell ourselves when the world feels chaotic and we need to impose order. We need to believe in the singular timeline to function. Imagine waking up every morning unsure if the past you remember actually happened. Imagine making a decision but suspecting that all other options are still happening somewhere else. It would be paralyzing. The mind needs closure. It needs the comfort of "this happened, and that is that." The clock's ticking reassures us. The past is settled. The present is fleeting. The future will arrive and then also become settled. One story, one you, one world. Breathe in this certainty. It is a comforting way to view the world. Feels solid like the floor beneath your feet. Feels consistent like the rising sun. But tonight, we are going to gently loosen our grip on this intuition. We are going to drift toward a different possibility, one that has kept physicists awake not with fear, but with a quiet, vibrating wonder. The comfort of the single timeline is also a cage, though a gilded one. It tells us that reality is thinner than it might be. It tells us that the universe makes choices, that it discards options, that it is fundamentally wasteful. But what if the universe is not wasteful? What if every possibility that can exist does exist somewhere, somehow? This is not a new question. Philosophers have asked it for millennia. What if I had done something different? Is the beginning of every regret, every daydream, every alternate history novel. But what if that question is not just psychological? What if it is physical? What if the road not taken is not metaphorical but actual, a real road being traveled right now by another version of you, in a reality that coexists with this one? Before you dismiss this as fantasy, consider that the clock you trust so deeply is itself a recent invention in human history. For most of our species' existence, we lived by the sun and the seasons. The idea of hours and minutes is artificial. The idea that now is universal took Newton to formalize. And Einstein broke it again, showing that now depends on where you are and how fast you're moving. Every time we look closer at time, it becomes stranger. So perhaps our intuition, strong as it feels, is simply the view from one limited perspective. Imagine, just for a moment, that the clock you hear is not ticking in isolation. Imagine that with every tick, the universe is not moving in a straight line, but blooming, like a flower opening infinite petals. Imagine that the road you are on is not a single path, but a tree branching endlessly, silently, and invisibly, right here in the room with you. Picture a tree in your mind, not a small tree, but an ancient oak. Its roots dig deep into the earth. Its trunk is thick and solid, but above, in the canopy, it branches, once, twice, 1,000 times. Each branch splits into smaller branches. Each twig holds a bud. From a distance, the tree looks like a single entity, but up close, it is a network of choices. Left or right, up or toward the light. Every fork is a decision made by growth and circumstance. Now imagine that tree is invisible. You are standing on one branch, unaware of the others. You can feel the solidity beneath your feet. You assume this branch is the whole tree. But above you, below you, beside you, other branches exist. Other versions of the journey. Other outcomes sprouting from the same trunk. They do not contradict you. They do not collide with you. They simply are on a different frequency, a different channel. The tree grows in silence. There is no cracking sound when it branches. No alarm bells when a new possibility splits off. The universe, if it is truly like this tree, would branch constantly billions of times per second, with every quantum event, every particle interaction, every tiny moment of potential becoming actual. And you would never hear it. You would only ever experience your own branch, your own narrow slice of the infinite canopy. This might sound overwhelming. How can the mind hold such an idea? But remember, you already live with vast complexities you cannot perceive. Right now, radio waves are passing through your body. Wi-Fi signals, cell phone towers, satellite communications. The air around you is thick with invisible transmissions. You cannot see them, hear them, or feel them, Yet they are there, carrying voices, images, data. The invisible does not mean the unreal. The universe is calm, even when it is strange. And tonight, we will walk through the strangest garden of all. Rest your mind here for a moment. Let the ticking fade into the background. Let the idea settle like snow. You do not need to believe it yet. You only need to hold the question, what if? What if every tick of the clock does not erase possibility, but multiplies it? What if reality is far richer, far fuller than we have been taught? Let that question be a soft pillow, and let us drift together into the answer. Feel the weight of your body sinking into the mattress. Feel the slow rise and fall of your chest. In this moment, you are here. This is your branch. This is your frequency. Whatever else might exist in the quantum foam, this moment, this breath, this darkness, this quiet belongs to you. And that is enough. For now, that is more than enough. The crack in our intuition did not happen with a loud explosion. It did not happen with a thunderclap or an earthquake. It happened in silence, on paper, and in the quiet hum of laboratories where light was being asked to explain itself. It began when we started looking at the very small. The atoms, the electrons, the photons, those tiny packets of light that allow you to see the world. Picture those early laboratories. Dim rooms with wooden tables, glass tubes glowing faintly in the dark, the smell of ozone and hot metal, scientists in wool suits, peering through spectroscopes, taking careful notes by candlelight. They were not looking for miracles. They were looking for precision. They wanted to understand why heated metals glow different colors, why electric current flows through some materials and not others, why the sun shines. These were practical questions, industrial questions. The world was electrifying. Cities were installing streetlights. Factories needed better materials. The telegraph was connecting continents. Science was the engine of progress, and the engine ran on certainty. Calculate, predict, build. That was the method. For centuries, science was the study of the predictable. If you throw a ball, you can calculate where it will land. If you heat water, you know when it will boil. This was the classical world, the world of the single clock. But in the early 20th century, as we peered deeper into the fabric of reality, the rules began to blur. Isaac Newton had given us the laws of motion. They worked perfectly for apples falling from trees and planets orbiting the sun. James Clerk Maxwell had unified electricity and magnetism into elegant equations. The universe seemed like a vast clockwork mechanism. Wind it up and you could predict its behavior forever. This was the dream of classical physics. Complete knowledge, perfect prediction. But then, quietly, anomalies began to accumulate. Little cracks in the cathedral of certainty. The first crack appeared in something as mundane as a hot oven. The history of this crack is worth tracing slowly because it helps us understand why physicists came to such strange conclusions. They did not want to believe in multiple worlds. They were not mystics or dreamers. They were practical people trying to understand how a light bulb works, how an atom holds together, why metals conduct electricity. They were asking engineering questions, but the answers kept pointing towards something impossible. It began with light. Is light a wave or a particle? For centuries, this was a debate. Thomas Young's famous experiment in 1801 seemed to settle it. Light was a wave. But then Einstein came along in 1905 and showed that light comes in little packets or quanta. It behaves like a particle. So which is it? The answer turned out to be both. And not just sometimes one, sometimes the other, but deeply, fundamentally both. Then came the electrons. These tiny bits of matter that orbit the nucleus of an atom were supposed to be like little planets. But they refused to behave. They didn't travel in neat ellipses. They jumped. They disappeared from one orbit and reappeared in another without crossing the space in between. This quantum leap was the first sign that the smooth, continuous world of the clock was an illusion. Physicists discovered something that shouldn't be possible. They found that a single particle, a tiny speck of matter, could be in two places at once. Not in a poetic sense, but in a literal, measurable sense. Before you look at it, an electron is not here or there. It is a wave of possibility. It is a ghost in a cloud of potential. It is here and there and everywhere in between simultaneously. This is the famous superposition. It is the first crack in the single story of the universe. It suggests that at its foundation, reality is not a single sharp point, but a haze of many possibilities.
Imagine a spinning coin.
Is it heads or tails? While it is spinning, it is a blur. It is a mixture of both states. In our large world, we know the coin is just moving fast. But in the quantum world, the electron really is in that blur. It hasn't decided yet. It is hovering in a state of pure potential. But here is the problem that ruined everything, or perhaps began everything. When we look at the electron, when we measure it, it snaps into place. The cloud vanishes. The wave collapses. The particle appears in just one spot. It is as if the universe knows it is being watched and quickly decides on a single story to show you. This is the measurement problem. Why does looking at something change it? Why does the fuzzy quantum world suddenly become the sharp, solid world of chairs and tables just because we open our eyes? Felt like magic. And science hates magic. For decades, this collapse was accepted as a brute fact, a mystery we just had to live with. We assumed that the other possibilities simply disappeared. They were erased, gone. This was the Copenhagen interpretation, named after the city where Niels Bohr worked. It was a shut up and calculate approach. Don't ask what's happening behind the curtain. Just trust the results. But the question lingered. Where did the other possibilities go? Did the universe really just delete them? Then, in 1957, a young student named Hugh Everett III looked at the math and asked a quiet, dangerous question. He asked, what if the wave never collapses? Everett was a brilliant, iconoclastic thinker. He looked at the Schrödinger equation, the fundamental equation of quantum mechanics, and saw that it didn't say anything about collapsing. It didn't say the other possibilities vanished. It said they continued. He suggested that when you measure the particle, you don't force it to choose. Instead, you become part of the system. The universe splits. In one branch of reality, you see the particle here. In another branch, equally real, equally physical, you see the particle there. Both versions of you exist. Both outcomes happen. But they can no longer see each other. This was the birth of the many worlds interpretation. It was the moment the single clock stopped being the only timekeeper. What feels fixed is often only familiar. And the familiar world of one outcome was suddenly just one thread in a vast, shimmering tapestry. Everett's idea was ignored for a long time. It was too big, too strange. Felt like fiction. He left physics in frustration and went to work for the defense industry. But the math was clean. The math didn't ask for permission to be strange. It just was. And tonight, we follow that math into the quiet dark. You might be thinking that this sounds like a dream, a fantasy for chalkboards and late-night philosophy. But the strange rules of quantum mechanics, the very rules that lead us to the multiverse, are not distant. They are humming in your pocket right now. Perhaps you imagine quantum physics as something that belongs in distant laboratories. Giant circular tunnels buried beneath Switzerland. Rooms cooled to near absolute zero. Scientists in white coats peering at incomprehensible screens filled with particle tracks. This is the image we carry. Quantum mechanics as exotic, remote, accessible only to specialists with decades of training. But the truth is gentler and more intimate than that. The quantum world is not locked away. It is here, now, in the warm glow of the screen beside your bed. It is in the quiet hum of electronics all around you. It is in every photon of light that enters your eye, every molecule of air that enters your lungs. We often think of quantum physics as something that happens only in billion-dollar particle colliders or deep inside stars. But the technology that defines our modern life, the microchip, is a quantum device. Think of your smartphone. It is a miracle of glass and silicon. Inside that phone are billions of transistors, tiny switches that control the flow of information. These switches are now so small that they are approaching the size of atoms. At this scale, electrons don't just flow like water in a pipe. They tunnel. Let us slow down here. Let us really understand what is happening inside that small rectangle of glass and metal you carry everywhere. The transistor, the basic building block of all modern computing, is a quantum machine. In the 1940s, the first transistors were the size of your thumb. Today, a single chip contains billions of them, each far smaller than a bacterium. A transistor is a switch. It controls whether electricity flows or doesn't flow, on or off, 1 or 0. This is how computers think, in binary, in yes or no questions asked billions of times per second. But when the switch is small enough, when the gate controlling the flow is only a few atoms thick, something strange happens. Classical physics says the electron should not be able to pass through, but quantum physics says it can. Quantum tunneling is a ghost-like ability. An electron encounters a barrier it shouldn't be able to cross. It doesn't have enough energy to climb over it. In a classical world, the world of balls and walls, it would bounce back. But in the quantum world, the electron borrows energy from uncertainty. It simply appears on the other side, passes through the wall as if it weren't there. Imagine standing in front of a brick wall. You don't have the strength to climb it. In the classical world, you are stuck. But in the quantum world, if you were small enough, you could press yourself against the wall and, with a certain probability, simply appear on the other side. You didn't climb. You didn't dig. You didn't break through. You just transitioned. This is tunneling. The mathematics describe it as the wave function leaking through the barrier. Part of your probability cloud extends to the other side. And since you are your probability cloud, part of you is already there. When the measurement happens, when reality chooses, sometimes you are on the far side of the wall. Quietly, without fanfare. This isn't a glitch. It is a feature. Flash memory, the kind inside your phone and your USB stick, uses this tunneling to trap electrons in a special gate. That's how it remembers your photos even when the power is off. Every time you save a selfie, you are relying on a particle walking through a wall. Think about that for a moment. The memory in your phone works because electrons tunnel through barriers they shouldn't be able to cross. Engineers exploit this quantum strangeness to create floating gates that hold charge for years. The data persists not because of mechanical locks or magnetic fields, but because of the delicate quantum probability of electrons being trapped in an energy well. Your phone's memory relies on this. The lasers that read data, the MRI machines in hospitals, the GPS satellites orbiting the Earth, they all rely on the math of the quantum world. Consider the GPS system. It relies on a constellation of satellites carrying atomic clocks. These clocks measure time by the vibration of atoms, specifically cesium atoms. The precision required is staggering. If these clocks drift by even a billionth of a second, your location on the map would be off by feet, soon by miles. An atomic clock doesn't have gears or springs. It listens to the heartbeat of an atom. Cesium-133, to be precise. This atom, when exposed to microwave radiation at exactly the right frequency, flips between two energy states. It flips 9,192,631,770 times per second, every single time.
Noberiaszczyn.
This is the definition of a second now. Not the swing of a pendulum, not the rotation of the Earth, but the quantum vibration of a single type of atom. The GPS satellites orbit about 12,500 miles above your head. They are moving fast, about 8,700 miles per hour. At that speed and at that altitude, time itself behaves differently. Einstein's relativity predicts that their clocks run slightly faster than ours because they are farther from Earth's gravity. But they also run slightly slower because they are moving so fast. The two effects nearly cancel, but not quite. If engineers didn't correct for these tiny discrepancies, your GPS would drift by miles every day. If we used only the sensible laws of the large-scale world, your GPS would drift by miles every day. The map on your screen would show you in the middle of a river when you are safe in your bed. We have to correct for the quantum behavior of the atoms in the clock, and we even have to correct for the bending of time caused by Earth's gravity, Einstein's relativity. It is a delicate dance of the very small and the very large. So when you open a map app and see the little blue dot showing exactly where you are on the street, you are witnessing the harmony of quantum mechanics and general relativity. You are seeing proof that the strange is real, that the equations are not just mathematical games but descriptions of how the world actually works. And what about the laser? The light that scans your groceries, plays your DVDs, and carries the internet through fiber optic cables? A laser is a quantum object. It is a collection of photons marching in perfect lockstep, a coherent wave of light. This coherence is only possible because of the quantum rules that govern how atoms release energy. A normal light bulb emits photons in all directions, at all different times, with all different energies. It is chaotic light, but a laser is different. In a laser, atoms are excited to a higher energy state, and then they are coaxed into releasing their photons all at once, all in the same direction, all with the same wavelength. This is called stimulated emission, and it relies on the quantum nature of atoms. The photons march together like soldiers in formation. This is why laser light is so intense and focused. This is why it can read the microscopic pits on a DVD or carry a conversation across an ocean through a thin strand of glass. The coherence, the sameness, the unity of the photons is a quantum phenomenon. Even the screen you might be looking at right now, if it is an LED or OLED screen, is based on quantum mechanics. The diodes emit light when electrons jump from one energy level to another inside a semiconductor. The color of the light depends on the size of the jump. Red photons carry less energy than blue photons. The entire spectrum of colors you see is a map of quantum energy transitions. Consider the MRI machine in a hospital. It is one of the most powerful diagnostic tools in modern medicine, and it is fundamentally a quantum device. MRI stands for magnetic resonance imaging. It works by aligning the spins of hydrogen atoms in your body, mostly in water molecules, and then listening to the faint radio signals they emit when they relax back to their natural state. The spin of an atom is a quantum property. It is not a literal spinning, but a kind of intrinsic angular momentum that has no classical analog. When doctors slide a patient into the MRI tunnel, they are placing that person inside a strong magnetic field. The hydrogen nuclei, just single protons, align with the field like tiny compass needles. Then, a pulse of radio waves flips them. When they flip back, they emit their own radio signals, and these signals are detected and turned into images of soft tissue, of the brain, of the heart. All of this is quantum mechanics at work. These technologies are proof that the blur is real. We build our civilization on the back of this fuzziness. We trust the math enough to fly planes by it and to send messages across the ocean with it. And if we trust the math when it tells us how to build a laser, we must listen when it whispers about what else might be true. The same equations that allow you to scroll through photos tonight also suggest that the reality you see is only a sliver of the whole. The device in your hand is a small, glowing artifact of a universe that is far deeper than it looks. It is a compass pointing toward the multiverse. Think about the humble transistor again. Every time it switches, every time an electron tunnels through a barrier, the quantum wave function is involved. And if the many worlds interpretation is correct, then every quantum event, every tunneling, every photon emission, every spin flip creates a branching. In one branch, the electron tunneled. In another, it didn't. Both outcomes are real, just on different channels. Your phone might be performing billions of quantum operations per second. Billions of moments where the universe splits. If Everett was right, your phone is not just computing in this world. It is computing across the multiverse, touching all the possible branches, and then decoherence isolates you into the branch where you see the result on your screen. This is not science fiction. This is the implication of taking quantum mechanics seriously. This is what the math suggests when you don't artificially insert a collapse to make the theory more comfortable. Reality branches quietly, without drama. It happens in the chips of your phone, in the fusion of the sun, and perhaps in the synapses of your sleeping mind. Feel the weight of the device beside you if it is there. Feel its warmth. That warmth is the byproduct of billions of electrons moving, tunneling, switching. It is the warmth of the quantum world doing its silent, invisible work. And if the multiverse is real, then that warmth is also the warmth of infinite branching, of reality proliferating quietly, filling every possible state. The universe is calm, even when it is strange, and the proof is in your hand. The proof is glowing softly in the dark. We are standing at the edge of this idea now. It is a vast ocean and the water is deep, but we will not rush. We will drift. Over the next hours, as your breathing slows and the day dissolves, we will float through the layers of this mystery together. Take a breath here, a slow one, in through the nose, out through the mouth. Feel your shoulders drop. Feel the weight of your head on the pillow. We have come a distance already, from the familiar ticking clock to the strange quantum world humming in your pocket. And we have further to go. But there is no hurry. Time, as we are learning, is more flexible than we thought. We have left the shore of intuition. We know the clock is not as simple as it sounds. We know the phone in your pocket proves the strangeness of the small. Behind us is the shore, the world of common sense, where time flows in one direction and reality is singular. That shore is still there. It has not disappeared. It is the world you will wake up to tomorrow. But tonight, we are exploring deeper waters. We are asking, what if the shore is just the edge of something much larger? Think of this journey as a descent. Not a frightening descent into darkness, but a gentle sinking into warmth. Like lowering yourself into a hot bath after a long day. The water surrounds you. The temperature soothes your muscles. You let go. That is what we are doing with these ideas. We are lowering ourselves into the mystery, letting it hold us, letting it warm us. First, we will wade into the why. We will look at what a multiverse actually is. Is it other bubbles floating in space? Or is it right here, superimposed over us like a radio signal we can't tune into? We will understand the difference between the many worlds of quantum mechanics and the vast cosmic inflation that creates distant universes far away. The word multiverse can mean many things, and that can be confusing, so we will be careful. We will separate the flavors. There is the quantum multiverse, Everett's branching tree, where every quantum event splits reality into parallel channels. This is the multiverse of the very small, the multiverse that happens in your phone, in every photon, in every atom. Then there is the cosmic multiverse, the bubble universes created by eternal inflation. These are not parallel realities in the same space. They are separate pockets of spacetime, born from the explosive expansion of the early universe, isolated from each other by vast, inflating gulfs. In this view, our entire observable universe, billions of galaxies, trillions of stars, is just one bubble in an infinite foam. Both ideas use the same word, multiverse, but they describe different kinds of multiplicity. One is about the splitting of quantum possibilities. The other is about the proliferation of entire cosmic regions. We will explore both, slowly, gently, like walking through a museum at night, pausing before each painting to let it speak. Then we will visit the history. We will walk quietly through the laboratories of the 20th century. We will sit with the physicists who first saw the ghost in the machine. We will look at the experiments that forced us to abandon the idea of a single, determined world. We will relive the shock of the double-slit experiment and the spooky confirmation of entanglement. History is important because it shows us that these ideas did not come from nowhere. They were not invented by science fiction writers or mystics. They emerged, reluctantly, from careful observation. Scientists did not want to believe in superposition or entanglement. They tested and retested. They looked for loopholes. They tried to prove the strangeness wrong. But the data kept insisting. We will meet the people behind the equations. Hugh Everett, who saw the branching and was dismissed. Niels Bohr, who built a pragmatic interpretation to avoid the philosophical abyss. Alain Aspect, who performed the Bell tests in the 1980s and proved that spooky action is real. These were real people drinking coffee, arguing in conferences, scribbling on chalkboards. They were not gods. They were explorers just like us. We will drift further out to the extremes, to the beginning of time itself, to the Big Bang, where the universe was smaller than an atom and where the quantum rules ruled everything. We will see how the seeds of the multiverse might have been planted in the very first fraction of a second. We will float through the concept of eternal inflation, imagining universes budding off like foam on a wave. The extremes are where the mind stretches, where the numbers become so large or so small that they lose their human meaning. A trillionth of a second. A universe expanding faster than light. Temperatures higher than the core of any star. But we will not let the numbers overwhelm us. We will translate them into images. Foam, seeds, blooming flowers. The universe may be extreme, but it is not cruel. It operates by rules, and those rules have a kind of elegance. We will see how Alan Guth and Andre Linde, working independently, realized that the early universe must have undergone a period of exponential expansion. This was not an optional add-on to the Big Bang Theory. It was necessary to explain why the universe looks the way it does. Flat, smooth, uniform in every direction. Inflation solved these problems. But it also predicted something wild. That inflation, once started, might never fully stop. That it might continue in some regions, forever, creating an endless cascade of new universes. We will encounter the paradoxes, the puzzles that make our heads spin if we move too fast. We will handle them gently, like fragile puzzles. We will ask, is there another you? Do your choices matter? How can so many worlds exist without colliding? And finally, we will arrive at the frontier, the edge of what we know, the place where science turns into humble silence. Paradoxes are not failures. They are invitations. They are the places where our intuition breaks down and we are forced to build new intuitions. The paradox of identity. If you split, which one is you? The paradox of choice. If every option is taken, does choosing even matter? The paradox of probability. Why do we experience one outcome if all outcomes happen? These questions have answers, tentative, evolving answers, but they also have a beauty in their difficulty. They remind us that reality is not simple. It is not a puzzle that snaps together neatly. It is a mystery that reveals itself layer by layer, and each layer opens onto more questions. This is not frustrating. This is the joy of being conscious in a universe that is endlessly surprising. And at the frontier, we will admit what we do not know. We will stand at the edge of the map and look out into the blank space where the old cartographers used to write, "Here be dragons." But instead of fear, we will feel wonder. Because not knowing is the beginning of discovery. Certainty is comfortable, but uncertainty is alive. You do not need to memorize this. You do not need to pass a test. You only need to float. Let the ideas wash over you like a warm tide. If you drift off to sleep, that is perfect. The universe will continue to branch whether you are watching it or dreaming of it. This is not a lecture. This is a lullaby. The science is real, the equations are true, but the purpose here is not to teach you to calculate. The purpose is to invite you into a larger view of reality, to let you feel the scale and the strangeness and the strange beauty of a universe that is far more interesting than we were told as children. If a sentence drifts past you and you don't catch it, that is fine. If a concept blurs into sleep, that is fine. Your unconscious mind will absorb what it needs. Dreams are their own kind of multiverse. Every night, You explore branching narratives, impossible physics, alternate versions of your life. Perhaps sleep is practice for the multiverse. Perhaps dreaming is how we touch the other branches. So rest here at the threshold. We are about to step deeper, but there is no urgency. The universe is not going anywhere, or rather, it is going everywhere in every possible direction, and we are carried along safely in the current that belongs to us. Breathe again. Let the air fill your lungs and then release. With each breath, you are participating in the quantum world. Oxygen molecules are tunneling through membranes. Electrons are hopping between atoms. Your body is a symphony of quantum events, each one a tiny branching, each one contributing to the vast tree of reality. You are not separate from the multiverse. You are made of it. You are woven into it. Every cell in your body is a quantum system. Every thought in your mind is an electrochemical cascade that rides on quantum rails. You are not an observer of this mystery. You are part of it. And now, gently, we continue. The universe is calm, even when it is strange. Let us begin with a picture, a simple mental image to hold in the dark.
Immagine a radio.
When you turn the dial, you hear a station. Maybe it is playing jazz. The music is clear. The trumpet is loud. It feels like the only reality inside that radio box. But intellectually, that the air around you is thick with other stations. There is a classical station, a news station, a pop station. They are all vibrating in the same space. Right now, passing through the walls, passing through you. Let us stay with this radio for a moment. Really picture it. An old radio, perhaps, with a physical dial. You turn it slowly. Static. Then music. Turn it more. Static again. Then voices. Each station is a world of sound, a complete narrative universe. The jazz station has its own history, the musicians who recorded it, the studio where it was captured, the listeners who love it. The news station has its own urgency, its own flow of information. The classical station breathes with the rise and fall of symphonies composed centuries ago. They occupy the same room. They bounce off the same objects, but they do not interact. They do not crash into each other because they are on different frequencies. They are decoherent from one another. To the jazz station, the classical station does not exist. It is silence. It is nothing. The radio waves are all there, all at once, passing through your body right now. They move at the speed of light. They have been traveling for hours or seconds, depending on where they originated. But until you tune in, they are invisible to you. They are potential. The radio does not create the music. It selects it. It filters out all the other frequencies and amplifies one. You become an observer of one channel. This is the best analogy for the quantum multiverse. It is not necessarily a collection of bubbles floating far apart in a black void, though that is one type of multiverse theory. The quantum multiverse, the one Hugh Everett saw, is right here. It is a superposition of realities occupying the same space, separated not by distance, but by consistency. Think about what here means. You are lying in a bed in a room. That room has dimensions, length, width, height. But according to quantum mechanics, that room is not just three-dimensional. It exists in what physicists call Hilbert space, an infinite-dimensional mathematical space where all possible quantum states exist simultaneously. Your room is not just your room. It is a superposition of all possible configurations of atoms, all possible arrangements of particles, all vibrating together in this vast mathematical space. When reality branches, it doesn't move somewhere else. It differentiates. Think of a coin spinning on a table. While it spins, it is a blur. It is both heads and tails. It is a wave of heads-tails. This is the quantum state. When it stops, in our classical view, it becomes just heads. But in the multiverse view, the spinning coin doesn't just stop. The universe splits into two layers. In one layer, the coin is heads. In the other, the coin is tails. Let us slow down even more with this coin. Imagine you are flipping it. Your thumb presses against its edge. Your muscles tense. The coin leaves your hand, spinning through the air. In that moment of flight, before it lands, quantum mechanics says the coin is in superposition. It is not that we don't know which side will land. It is that the coin genuinely has not chosen yet. The wave function includes both outcomes, both histories woven together. When the coin hits the table, something profound happens. The quantum state interacts with the table, with the air molecules, with the photons bouncing off its surface. This interaction is called decoherence. The superposition doesn't collapse into one outcome and erase the other. Instead, the universe bifurcates. It splits into two non-communicating branches. In one branch, you see heads. In the other, you see tails. Both are real. These layers drift apart. They stop interacting. They become like the different radio stations. The version of you that sees heads cannot hear the version of you that sees tails. The you that exists before the coin lands is the trunk of the tree. The you that sees the result is a branch. But what does drift apart mean? It is not a physical separation in space. The two versions of you are still in the same room, occupying the same coordinates. But they are now on different frequencies of the wave function. The probability amplitudes that describe you seeing heads and you seeing tails have become orthogonal. They no longer overlap in the mathematics. You cannot interfere with the other version of yourself because your quantum states no longer share any common terms in the equation. This is called decoherence. It is a gentle word for a profound separation. It explains why we only see one world. We are trapped inside one frequency. We are consistent with only one version of history. But the math suggests the other frequencies are still there, humming in the silence, carrying on with their own stories.
Decoherence happens incredibly fast.
For macroscopic objects the size of coins or people, decoherence occurs in tiny fractions of a second. This is why we never see superpositions in daily life. By the time a photon hits your eye, by the time a nerve fires in your brain, the branching has already happened. You are already on one branch, isolated from the others. Imagine a library with infinite books. But instead of the books being on shelves, they are all in the same spot, superimposed. When you open one, you are tuning in to that specific story. The other stories are still there, written in invisible ink, occupying the same pages, but you can only read one at a time. Now let us try another image. Imagine a river that forks. Before the fork, there is one flow. The water is unified. It moves as a single body. But then the river reaches a rock or a split in the land, and it divides. One branch flows left, the other flows right. From above, you can see both branches. But if you are a fish in the left branch, you have no knowledge of the right branch. To you, it is as if the right branch does not exist. You swim forward in your current, unaware that the river you came from has multiplied. The many worlds interpretation says that this forking happens at every quantum event. Every time a particle is measured, every time a wave function chooses, the river splits. Not just twice, but into as many branches as there are possible outcomes. A photon could be absorbed by your eye or miss it entirely. An electron could tunnel through a barrier or bounce back. Each possibility becomes its own branch. And because there are trillions upon trillions of quantum events happening every second, in your brain, in the air, in the light around you, the universe is branching constantly. The tree of reality is growing at an unimaginable rate. Every moment births countless new branches. So what it really is a fullness. The universe is not empty space with a few things in it. It is a saturated state of infinite possibility, where everything that can happen does happen, just on a different channel. Think of it as a kind of cosmic democracy. No outcome is privileged. No possibility is erased. Every potential future gets its chance to exist. The universe does not choose favorites. It explores all paths simultaneously, and we, as conscious observers, ride along one path, experiencing the illusion of a single history. But here is the comforting part. your experience is real. The branch you are on is as real as any other. You are not in a lesser reality or a shadow reality. You are in a full, complete universe. The fact that there are other branches does not diminish yours. If anything, it enriches the whole. Your joys, your sorrows, your choices, they all matter. They all contribute to the vast tapestry. Some people find this idea unsettling. If every possibility happens, does my choice matter? Yes, it does. Because the version of you making the choice is real. The consequences you experience are real. The love you feel, the friendships you build, the work you do, all of it is genuine. The existence of other branches does not make your life less meaningful. It makes the universe more generous. Let us return to the radio analogy one more time. You are tuned to one station. That station is playing your life. The music is yours. The story is yours. The fact that other stations exist, playing different songs, does not diminish the song you are hearing. It does not make your music less beautiful. You are not required to listen to all the stations at once. You are allowed to be here now in this one frequency and to find it sufficient. Recap gently. We have moved from the ticking clock of one reality to the radio stations of many. We understand that the other worlds might not be far away, but simply out of tune with us. The universe is calm, even when it is strange. Breathe here. Let the air fill your lungs and release. You are in one branch of the tree. You are tuned to one frequency, and that is enough. The other branches take care of themselves. They do not need your attention. They do not require your energy. You are free to simply be here in this moment, in this version of now. How does that feel? To think that the space you occupy is full of shadows of what might have been. Perhaps it feels strange. Perhaps it feels liberating. Perhaps it makes the room seem larger, as if the walls have receded into a deeper space. Or perhaps it changes nothing. The pillow is still soft. The darkness is still kind. And you are still here, safe, drifting gently towards sleep. The multiverse, if it exists, is not a burden to carry. It is not a puzzle you must solve. It is simply the way things are, a fuller, richer picture of reality than we were taught. And knowing it or not knowing it does not change the gentle rhythm of your breath, the slow descent into rest. Let the concept settle like sediment in water. Let it drift to the bottom of your awareness. You do not need to hold it tightly. You do not need to understand every detail. The universe is vast and strange and beautiful, and you are a part of it. That is the only certainty you need. And now we move forward gently to see how we know what we know. Science is conservative. It does not like to make up ghost stories. It only accepts the strange when the simple refuses to work. Let us look at the moments when the simple refuse to work. This conservatism is not stubbornness. It is wisdom. Science has learned, through centuries of false starts and dead ends, to be skeptical of the spectacular, to demand evidence, to repeat experiments, to eliminate every other explanation before accepting the impossible. So when physicists tell us that reality is strange, we can trust that they fought against that conclusion as long as they could. The most famous crack in the wall is the double-slit experiment. It is the classic mystery. Imagine a wall with two vertical slits cut into it. Behind it is a screen. If you fire bullets at the wall, you get two bands of hits on the screen. Simple. Bullets go through the left slit or the right slit. They land in two neat piles. Picture this in your mind. A solid wall, perhaps metal or wood, with two narrow openings. Behind it, a screen that records where things hit. You stand at a distance and fire a machine gun at the wall. Most bullets hit the wall and stop, but some pass through the left slit. Some pass through the right slit. They leave marks on the screen, two bright patches, directly behind each slit. This is classical physics. This is the world of the clock. Everything has a definite path. But if you fire electrons, tiny bits of matter, something eerie happens. Instead of two bands, you see an interference pattern, a series of stripes, dark, light, dark, light. This pattern only happens if waves collide with each other. It means the electron went through the left slit and the right slit simultaneously. It interfered with itself. It was a ghost wave. Let us pause here. Really absorb this. An electron is a particle. It has mass. It has charge. You can count electrons. 1, 2, 3. But when you send them through two slits, they behave like waves. And not like a stream of waves, but like each individual electron is a wave that passes through both slits at once. Imagine throwing a rock into a pond with two gates. The ripples go through both gates and overlap on the other side. Where the peaks meet, the water goes high. Where a peak meets a trough, the water goes flat. That is interference. But we are talking about particles of matter. The electron is acting like a wave of pure potential. The interference pattern tells us something profound. If the electron went through only one slit, we would see two bands. But we see many bands, bright stripes separated by dark stripes. The bright stripes are where the electron waves from both slits arrive in phase, reinforcing each other. The dark stripes are where they arrive out of phase, canceling each other. This only makes sense if each electron somehow knows about both slits. But wait, if we put a detector, a mechanical eye, by the slits to see which one the electron actually goes through, the pattern vanishes. The electron suddenly behaves like a bullet again. Two bands.
No interference.
The act of watching changed the outcome. This experiment has been done thousands of times with electrons, photons, even large molecules. The result is always the same. Reality is fluid until it interacts with a measurement. This is not a malfunction of the equipment. It is not a mistake. It has been tested with every conceivable variation. You can send the electrons one at a time, waiting hours between each one, and the interference pattern still builds up. Each single electron, traveling alone, somehow interferes with itself. It is as if the electron is in two places at once, exploring both slits, until we force it to reveal which path it took. This experiment suggests that the electron explores all possible paths. In the many worlds view, the electron actually goes through the left slit in one universe and the right slit in another. When the universes overlap before measurement, they interfere. When we measure, we isolate ourselves in one universe so the interference stops. Think about what this means. The electron does not decide which slit to use. It uses both. The universe does not choose. It branches. One branch has the electron going left. The other branch has it going right. And because both branches are part of the same quantum state before measurement, they can interfere with each other. The interference pattern is the shadow of the other branch, the echo of the path not taken in your world but taken in another. Physicists have even done delayed choice versions of this experiment. You can decide whether to measure which slit the electron went through after it has already passed through the slits but before it hits the screen. The universe seems to wait for your decision. If you choose to measure, you get two bands. If you choose not to, you get interference. The past is not fixed until you observe it. Or rather, all pasts are real, and you are choosing which branch to inhabit. Now breathe. This is heavy. It challenges everything we think we know about cause and effect, about the flow of time, about the solidity of the past. But notice, the universe is still here. The experiment is calm. The electrons do not scream as they split. They simply follow the mathematics quietly, reliably, every single time. Then, decades later, came the Bell test experiments. In the early 1980s, and confirmed with loophole-free precision in 2015, physicists proved that spooky action at a distance is real. They showed that two particles, once linked, share a destiny even if they are miles apart. If you measure one, the other responds instantly, faster than light, instantaneously. This story begins in 1935 with Einstein, Podolsky, and Rosen. They wrote a paper arguing that quantum mechanics must be incomplete. They described a thought experiment where two particles are created together in a specific quantum state, entangled. Then they are separated by a great distance. Quantum mechanics predicts that measuring one particle instantly affects the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance and argued it was absurd. Information cannot travel faster than light. So he concluded there must be hidden variables, some deeper reality determining the outcomes in advance. For decades, this remained a philosophical debate. Then, in 1964, physicist John Bell showed that you could test it. He derived an inequality, a mathematical relationship that must hold true if hidden variables exist. If the inequality is violated, then quantum mechanics is right, and the universe really is non-local. The particles really are connected instantaneously. In 1981, Alain Aspect and his team in France performed the first convincing Bell test. They used entangled photons and measured their polarizations. The results violated Bell's inequality. The universe was non-local. The photons were communicating faster than light. Or rather, they were not separate entities, they were part of a single quantum system, a single wave function stretched across space. But skeptics pointed out loopholes, ways the experiment might be fooled. Maybe the detectors were communicating with each other. Maybe the photons were choosing which detector to go to. For decades, physicists worked to close every loophole. Finally, in 2015, 3 separate teams performed loophole-free Bell tests. One in Delft, Netherlands. One in Vienna, Austria. One in Boulder, Colorado. All confirmed the same result. Quantum entanglement is real. The universe is non-local. This broke the idea of local realism. The idea that things only exist right here, right now, independent of everything else. It proved that the universe is deeply connected in ways we cannot see. It pushed us further toward the idea that the underlying reality is a vast, interconnected wave function, a single mathematical object that contains all possibilities. What does this mean for the multiverse? In the many worlds interpretation, entanglement is natural. When two particles are entangled, they are part of the same quantum state. When you measure one, you don't send a signal to the other. Instead, the universe branches. In one branch, you measure up, and the other particle is down. In another branch, you measure down, and the other is up. The correlation is perfect because the branching is deterministic. The particles are not communicating. They are simply following the same script in different parts of the wave function. These experiments are the bedrock. They are not theories. They are data. They tell us that the world of the single clock is an illusion of our perspective. The data whispers that the world is vast, branching, and interconnected. There are other experiments, too. The quantum eraser experiments, where you can erase the information about which path a particle took and restore the interference pattern, even after the particle has already landed. This suggests that the past is not fixed, that it remains in superposition until a final measurement collapses it. Or, in the many worlds view, until decoherence isolates you into one branch. There are experiments with large molecules, chains of hundreds of atoms, showing interference patterns. These are not subatomic particles. These are almost visible objects, and yet they still act like waves, still explore multiple paths simultaneously. The quantum world is not limited to the invisibly small. It is the foundation of all scales. Scientists have even done experiments testing the nature of time itself. They have sent photons into the past in a controlled way using clever arrangements of mirrors and detectors, and shown that the future can influence the past. Not in a way that creates paradoxes, but in a way that is consistent with quantum mechanics. The timeline is not as linear as it feels. What feels fixed is often only familiar. And the familiar view of bullets and walls is just a blurry approximation of the true, shimmering quantum world. Let all of this settle gently. You do not need to understand every detail. You do not need to visualize the wave function or calculate the probability amplitudes. You only need to feel the weight of the evidence. Thousands of experiments, decades of careful work, skeptics becoming believers, the universe insisting over and over that it is stranger than we imagined. And in that strangeness is a kind of beauty. The universe is not arbitrary, it follows rules. But the rules are deeper and more elegant than the surface simplicity we experience. Reality is a symphony, and we have been listening to only one instrument. Now we are beginning to hear the full orchestra. Recap softly, we have seen the double-slit experiment where particles act like waves. We have seen Bell tests, where entangled particles prove that the universe is non-local. We have seen that measurement changes reality, not because we are special, but because observation is interaction, and interaction is branching. The experiments changed our minds because they gave us no choice. The data is clear. The universe is quantum, and quantum means possibility, superposition, and perhaps multiplicity. Rest here. Let the experiments fade into the background. You have touched the evidence. You have felt the weight of proof. Now let it go. Let it dissolve into the gentle dark. The universe will continue to follow its rules whether you are thinking about them or dreaming of something else entirely. Let us drift now from the tiny electron to the impossibly huge. The universe pushes back when we go to the extremes, but it pushes gently, like water resisting your hand as you move it through a warm bath. There is pressure, but there is also beauty in the resistance. We have been dwelling in the small, the quantum realm where particles tunnel and waves collapse. We have been exploring the intimate scale of atoms and photons, where a single electron can be in two places at once, where measurement changes reality, where the wave function governs all. But the multiverse does not live only in the microscopic. It also lives in the vast, in the cosmic. In the first moments of creation itself, when the universe was smaller than an atom yet contained everything that would become stars, galaxies, and us. Picture yourself zooming out. Imagine pulling back from your body, through the ceiling, through the roof, up past the clouds. The city below becomes a grid of lights. The continent becomes a curve. The planet becomes a blue marble suspended in blackness. Pull back further. The moon appears. Mars. Jupiter with its swirling storms. The asteroid belt. Neptune at the edge of the solar system. And then the sun itself becomes just one star among billions. The Milky Way stretches across space like a spiral of light. 400 billion stars. Countless planets. Vast clouds of gas and dust where new stars are being born. Black holes lurking in the center. And if you pull back even further, the galaxy shrinks to a speck. You see other galaxies. Clusters of galaxies. Superclusters. Filaments of matter stretching across billions of light years, forming a cosmic web. And between the filaments, vast voids, regions of space so empty that a single galaxy would be lonely. This is the observable universe, 93 billion light-years across, containing perhaps 2 trillion galaxies, each galaxy containing billions or trillions of stars. The numbers are so large they lose meaning. But the feeling is clear. We are very, very small, and the universe is very, very large. We look up at the night sky. It is black and speckled with stars. It looks static. It looks eternal. The constellations our ancestors memorized thousands of years ago still hang in the same patterns. The Big Dipper, Orion's belt with its 3 bright stars in a row. The Pleiades, that delicate cluster the Greeks called the Seven Sisters. Cassiopeia shaped like a W. These patterns seem fixed, like diamonds sewn onto a velvet curtain that has hung unchanging since the dawn of time. Our ancestors looked at the same stars. The ancient Egyptians used them to align the pyramids. The Polynesians navigated by them across the Pacific. The Mayans built observatories to track their movements. For thousands of years, humans assumed the stars were eternal, fixed to crystal spheres that rotated around the Earth. Even when Copernicus placed the sun at the center, even when Galileo's telescope revealed mountains on the moon and moons around Jupiter, the stars themselves seemed unchanging. But we know better now. We know it is expanding. The galaxies are rushing away from us, and not just drifting but fleeing, as if propelled by some ancient explosion. This discovery changed everything. It forced us to accept that the universe has a history, that it was born, that it will die, that we are living in a specific chapter of a much longer story. In the 1920s, Edwin Hubble, working at the Mount Wilson Observatory in California, using the largest telescope in the world at the time, looked through the eyepiece and measured the light from distant galaxies. He was looking for something specific: the spectrum of light, the rainbow of colors hidden in the starlight. When you pass light through a prism, it splits into its component wavelengths. And embedded in that spectrum are dark lines, absorption lines, where specific elements have absorbed specific colors. These lines are like fingerprints. Hydrogen always absorbs the same wavelengths. Helium has its own pattern. Oxygen, carbon, iron, each element leaves its mark. So when Hubble looked at light from distant galaxies, he could identify which elements were there. But he noticed something strange. The lines were shifted. They were all pushed toward the red end of the spectrum. Redshifted. This meant the galaxies were moving away. It is the same effect as the Doppler shift you hear when an ambulance passes you. As it approaches, the siren sounds higher in pitch. As it recedes, the pitch drops. Light behaves the same way. If a source of light is moving toward you, the light is blue shifted, compressed toward shorter wavelengths. If it is moving away, the light is redshifted, stretched toward longer wavelengths. Hubble found that the farther away a galaxy is, the faster it recedes. This was the first solid evidence that the universe is not static. It is expanding. It is growing. And if it is growing now, it must have been smaller in the past. Much smaller. This was the seed of the Big Bang Theory. Imagine rewinding time. The galaxies draw together. The space between them shrinks. The universe becomes denser, hotter. Stars merge. Atoms break apart into their components: protons, neutrons, electrons. Then even those dissolve into a soup of quarks and gluons. The temperature rises to billions of degrees, then trillions. The entire observable universe, everything we can see, 93 billion light-years across, containing hundreds of billions of galaxies, compresses down to the size of a grapefruit, then smaller, the size of a marble, a grain of sand, an atom, a nucleus, a quark. At this scale, the distinctions between matter and energy blur. Space and time lose their meaning. The temperature is so high that particles and antiparticles spontaneously pop into existence and annihilate in flashes of pure energy. This is the realm of quantum gravity, where the smooth fabric of spacetime dissolves into a foam of possibility. And then 13.8 billion years ago, there is a moment so hot, so dense, so extreme, that our equations break down. This is the Big Bang, not an explosion in space, but an explosion of space itself. Not a bomb going off at a location, but the sudden emergence of all locations, all space, all time, from a singularity of infinite density and temperature. The Big Bang is not a place. You cannot point to where it happened and say, there. It happened everywhere. Every point in space today was once part of that primordial fireball. The room you are in right now, the air, the walls, the atoms in your body, all of it emerged from that initial explosion. You are made of stardust, yes, but before that, you are made of Big Bang material. You are ancient. This is the first extreme. The universe was once unimaginably small and unimaginably hot. The temperature was trillions of degrees. The density was infinite. And from this singularity, everything we see emerged. But how? And more importantly for our story tonight, why does the universe look the way it does? Why is it so smooth? Why is it so flat? Why does it seem fine-tuned for life? In the early 1980s, physicists like Alan Guth and Andre Linde were puzzling over these questions. They looked at the universe we observe and noticed something strange. The universe is remarkably uniform. If you point a telescope in one direction and measure the temperature of the cosmic microwave background, the faint glow left over from the Big Bang, you get a number, about 2.7 Kelvin, just a few degrees above absolute zero. If you point the telescope in the opposite direction 180 degrees away, you get the same number, to within 1 part in 100,000. This is the horizon problem. Those two regions of space are so far apart that light from one could never have reached the other in the time since the Big Bang. They are causally disconnected. Information travels at the speed of light, and there simply hasn't been enough time for the two regions to communicate, to exchange heat, to equilibrate. So how did they agree to have the same temperature? It's like finding two people on opposite sides of the planet wearing the same obscure outfit, despite never having communicated. How did they coordinate? And there was another puzzle called the flatness problem. The geometry of the universe, the way space curves, is incredibly flat. In general relativity, space can be curved by mass and energy. A massive object like the sun curves space around it, causing planets to orbit. But on the largest scales, the universe appears to be flat. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. This flatness is not guaranteed. If the universe had even slightly more energy at the beginning, it would have curved positively, like the surface of a sphere, and eventually collapse back on itself. If it had slightly less energy, it would have curved negatively, like a saddle, and flown apart so fast that stars could never form. The fact that we exist in a universe that is flat to within 1 part in a trillion is like balancing a pencil on its tip and finding it still upright a billion years later. It requires explanation. Alan Guth, working late one night in December 1979, had an insight that would change cosmology. He was thinking about particle physics, about phase transitions in the early universe, about how forces might have unified at high temperatures and then separated as the universe cooled. And he realized something astonishing. What if, in the first tiny fraction of a second after the Big Bang, the universe didn't just expand, it inflated? What if space grew exponentially, doubling in size every trillionth of a second? In less than a blink, in a time interval so short that light could not cross the width of a proton, the universe would have expanded by a factor of 10 to the power of 30 or more. A grain of sand would become larger than the observable universe today. A region smaller than an atom would stretch to encompass everything we can see. This is cosmic inflation. The word inflation was borrowed from economics, the idea of rapid, exponential growth. Guth scribbled in his notebook, "Spectacular realization." He knew he had found something big. His paper, published in 1981, was titled The Inflationary Universe, a possible solution to the horizon and flatness problems. It was modest in tone, but revolutionary in implication. Andrei Linde, working independently in the Soviet Union, developed similar ideas around the same time. He refined the theory, proposing variations like chaotic inflation, where different regions of space inflate at different rates depending on the initial conditions. Together, Guth and Linde laid the foundation for what is now the leading theory of the early universe. Inflation is no longer a fringe idea. It is the standard model of cosmology, supported by decades of observations. Inflation solves the puzzles. If a tiny patch of space inflated to become our entire observable universe, then all parts of that patch were once close together, close enough to exchange heat and reach the same temperature. That solves the horizon problem, and the act of inflating stretches any curvature flat, like pulling a wrinkled bedsheet tight. That solves the flatness problem. Inflation also explains the seeds of structure, the tiny quantum fluctuations that, stretched to cosmic scales, became the density variations that eventually grew into galaxies. Imagine a balloon with tiny wrinkles on its surface. If you blow it up just a little, the wrinkles remain. But if you inflate it to the size of a house, to the size of a planet, to the size of the solar system, the wrinkles vanish. The surface appears smooth. This is what inflation did to the universe. It took whatever chaotic, lumpy, wrinkled state existed at the very beginning and stretched it into the smooth, flat cosmos we observe today. But here is where the story takes a turn toward the multiverse. Here is where the extremes reveal their secret. Inflation does not just happen once, cleanly, and then stop everywhere at the same time. The field that drives inflation, the inflaton field, a hypothetical form of energy that pervades space, is subject to quantum fluctuations. Remember, at the quantum level, everything is uncertain. Everything vibrates. Everything is a wave of probability. In some regions of the inflating space, the inflaton field decays. The energy that was driving the exponential expansion converts into ordinary matter and radiation, electrons, photons, quarks, all the particles that make up the universe we know. Stars form. Galaxies coalesce. Life eventually emerges. This is what happened in our region, our bubble of the multiverse. Inflation ended here 13.8 billion years ago, and the universe we call home began its slower, decelerating expansion. But in other regions, the inflaton field does not decay, keeps inflating. And because inflation is exponential, those regions grow faster than the regions where inflation has stopped. Imagine a race where one runner adds 1 step per second, but another runner doubles their speed every second. The second runner will soon leave the first in the dust, then in a different city, then on a different continent, then in a different galaxy. Exponential growth is relentless. So even though inflation ended in our bubble 13.8 billion years ago, in the vast majority of the multiverse, inflation is still happening. Right now, forever. This is eternal inflation. Once inflation starts, it never fully stops. It continues in some regions, creating more and more space, which in turn provides more opportunities for new bubbles to form. The process is self-perpetuating. Inflation creates space faster than pockets can form. It is a cosmic fractal, a never-ending cascade of universe creation. Picture a loaf of bread rising in an oven. As the dough heats, yeast produces gas. Bubbles form inside the dough. Each bubble is a pocket where the gas is collected, where the dough has stopped expanding and solidified into a structure. Our universe is one such bubble. We live inside it. The walls of our bubble are the limits of what we can see, the edge of the observable universe. But the dough around it, the inflating space outside our bubble, keeps rising. More bubbles form. Each bubble is a universe with its own Big Bang, its own history, its own galaxies. And the dough between them continues to stretch, creating more space, more bubbles, endlessly. Or imagine ocean foam. You stand on the beach and watch a wave crash onto the shore. For a moment, the water is white with bubbles, thousands of tiny spheres, each with its own thin membrane separating the air inside from the water outside. Some bubbles pop immediately, bursting back into the sea. Some last a few seconds, glistening in the sunlight before they collapse. Each bubble is a separate world, holding a pocket of air, surrounded by water, temporary and fragile. Now imagine that the ocean never stops frothing, that the foam goes on forever, in all directions, bubbles within bubbles, layers upon layers. Some bubbles merge, some split. The foam is dynamic, constantly changing, but always producing more bubbles. This is the bubble multiverse. Our universe is one bubble in an infinite froth. This is the bubble multiverse, or inflationary multiverse. In this view, reality is an infinite foam of universes. Our observable universe, the 93 billion light-years of space we can see, containing hundreds of billions of galaxies, trillions of stars, uncountable planets, is just one bubble, one finite pocket in an infinite sea. And in this view, each bubble might have different properties, different laws of physics, different values for the fundamental constants that govern how matter and energy behave. Why? Because the laws of physics as we experience them might not be fundamental. They might be emergent, the result of how the inflaton field decayed, how the symmetries broke, how the forces crystallized as the universe cooled from its initial inferno. Think of water freezing into ice. Depending on the temperature and pressure, water can form different crystal structures. Hexagonal ice, cubic ice, dozens of exotic forms. The same underlying substance, but different arrangements. Similarly, the inflaton field might settle into different configurations in different bubbles. In one bubble, gravity might be stronger. Stars would burn faster, exhaust their fuel sooner, collapse into black holes before planets could form stable orbits. Life as we know it might be impossible. In another bubble, the electromagnetic force might be weaker. Atoms would be larger, less tightly bound. Chemistry would be different. Molecules might not form. In yet another bubble, there might be more than 3 dimensions of space, or time might flow in multiple directions, or matter and antimatter might have formed in equal amounts, annihilating each other completely, leaving an empty void. This is not science fiction. This is a consequence of taking inflation seriously. If the inflaton field is subject to quantum fluctuations, and if those fluctuations can cause different outcomes in different regions, then the multiverse is not optional. It is inevitable. It is the natural result of combining quantum mechanics with the theory of cosmic inflation. Once you accept that space can inflate exponentially, and that quantum uncertainty allows for different inflation rates in different regions, the multiverse follows as a logical conclusion. Some physicists find this idea troubling. It means that the laws of physics we have worked so hard to discover, the speed of light, the strength of gravity, the charge of the electron, the mass of the proton, might just be local bylaws, specific to our bubble. They are not universal truths inscribed in the fabric of reality. They are environmental conditions like the temperature of Earth or the salinity of the ocean. In another bubble, those numbers could be different. The universe next door might operate by entirely different rules. This seems to undermine the search for a theory of everything, a single elegant equation that explains all of reality. For centuries, physicists have assumed that beneath the complexity of nature lies a simple, beautiful mathematical structure. Newton's laws, Maxwell's equations, Einstein's relativity, the standard model of particle physics, each was a step toward that ultimate theory. But if reality is an infinite foam with infinite variety, how do we make sense of it? How do we find the one true equation if there is no one true universe? Others find it liberating. The multiverse offers an answer to one of the deepest mysteries in science: fine-tuning. The universe we inhabit seems exquisitely calibrated for life. The strength of the nuclear forces, the mass of the electron, the rate of cosmic expansion, the ratio of matter to antimatter, all of these are precisely balanced. If any one of them were slightly different, stars would not form, or atoms would not hold together, or the universe would have collapsed before life could emerge, or it would have expanded so fast that galaxies never coalesced. The odds against this fine-tuning are astronomical. It is like shuffling a deck of cards and dealing a royal flush 10 times in a row. It demands explanation. Some have argued that this fine-tuning points to design, to a creator who carefully set the dials to allow for life. Others have dismissed it as coincidence, or argued that we don't yet understand the deeper principles that might constrain these values. The multiverse offers a third answer. In an infinite foam of bubbles, all possible values of these constants are realized somewhere. Most bubbles are sterile, too hot, too cold, too unstable, too empty. But a tiny fraction have conditions that allow for stars, planets, chemistry, biology, consciousness. We find ourselves in one of those rare bubbles not because it was designed for us, but because we could only exist in such a bubble. This is the anthropic principle. We observe a life-friendly universe because we are alive to observe it. In the dead bubbles, there is no one to ask the question. It is a selection effect, like asking why you were born in a hospital rather than on a deserted island. Hospitals are where births happen. Life-friendly universes are where observers happen. The multiverse makes this inevitable. Somewhere in the infinite foam, the conditions are right. And that somewhere is here, for us. We are like ants living on a single bubble in a vast, soapy foam. We cannot see the other bubbles because the space between us and them is expanding faster than light. This isolation is not a limitation of our telescopes or our technology. It is a fundamental feature of the cosmos. Light from another bubble will never reach us. Not in a billion years. Not in a trillion. The space between bubbles is inflating, creating new space faster than light can cross it. This does not violate relativity. Nothing is moving through space faster than light. Space itself is expanding. A photon emitted from our bubble toward another would be carried backward by the expansion, like a swimmer trying to reach the far shore while the river itself is lengthening. The swimmer swims forward, but the destination recedes faster. The photon travels at light speed, but the space it is crossing is growing faster than it can travel. We are surrounded by other universes, but we can never touch them, never see them, never communicate with them. They are as unreachable as the past. Breathe here. Let that image settle. You are in one bubble of an infinite foam. Your life, your planet, your galaxy, all contained in one tiny pocket of a much larger reality. It is humbling, yes, but it is also strangely comforting. You are not responsible for the whole foam. You are only responsible for your bubble. And your bubble is beautiful. Your bubble has stars and oceans and mountains and forests and music and love and sleep. And what of the wave function of the universe? This is where the quantum and the cosmic meet in a profound embrace. In the 1980s, Stephen Hawking and James Hartle asked a bold, almost audacious question. Can we apply quantum mechanics to the universe as a whole? Can we write a wave function, not for a single electron, not for a pair of entangled photons, but for all of space and time, for the entire cosmos? Normally, quantum mechanics describes small systems. An atom in an excited state, a photon passing through a slit, a pair of particles entangled by a common origin. The wave function tells you the probability of finding the system in one state or another. It is a tool for the microscopic world. But Hawking and Hartle proposed that the entire universe is also a quantum system. The Hartle-Hawking state, or no-boundary proposal, treats the cosmos as a single quantum object, a wave function that encompasses everything. If you do that, the math suggests something astonishing. The universe didn't have a single, definite beginning. Instead, it had every possible beginning, every possible initial condition, every possible way the Big Bang could have unfolded, every possible value for the density, the temperature, the distribution of matter, the quantum fluctuations. All of these potential histories exist in superposition, and they all contribute to the now we experience. Imagine you are watching a river. You see the water flowing past your feet. It is clear and cold. You can ask, where did this water come from? You can trace it upstream, through tributaries, through mountain streams, through rain that fell weeks ago, through snow that melted in the spring. But what if the river had 1,000 sources? What if every possible path that could lead to this moment actually did lead to this moment all at once, superimposed? That is what the wave function of the universe suggests. The present is the sum of all possible pasts. Hawking and Hartle proposed the no-boundary proposal. Imagine asking, what came before the Big Bang? The question assumes there is a before. But if time itself began at the Big Bang, then before has no meaning. It is like asking what is north of the North Pole. The question makes grammatical sense but is physically nonsensical. There is no north once you reach the pole. Similarly, there is no before once you reach the Big Bang. Hawking's answer was elegant. The universe has no boundary in time. Time itself smoothly emerges from a quantum state that has no before or beginning in the classical sense. He used a mathematical trick called imaginary time. Not imaginary in the sense of made up, but imaginary as in involving the square root of -1, a number that appears throughout quantum mechanics and relativity. In imaginary time, the distinction between time and space blurs. The universe has no edge, no boundary, no moment of first creation. It simply is. It is finite but unbounded, like the surface of a sphere. If you walk east on Earth, you never reach an edge. You eventually return to where you started. The surface is finite, but it has no boundary. Similarly, in Hawking's formulation, the universe is finite in time, but it has no temporal boundary, no first moment, just a smooth, self-contained structure. In this view, the universe creates itself, not through magic or divine intervention, but through quantum tunneling, the same ghost-like process that allows electrons to pass through barriers in your smartphone. The universe tunnels into existence from nothing, or rather, from a quantum foam of spacetime possibilities. It is a self-consistent loop, where the end conditions determine the beginning conditions in a vast, closed curve of causation. The universe is its own explanation. This idea is almost impossible to visualize. It requires thinking in 4 dimensions or more. It requires letting go of the idea that time has a clear arrow, a definite direction, a single path from past to future. But the mathematics works. It produces predictions that match what we observe, the smoothness of the universe, the patterns in the cosmic microwave background, the distribution of galaxies. And it suggests, once again, that the singular story, the one timeline, the one universe, the one history is an approximation. A useful fiction we tell ourselves to navigate daily life. Quantum cosmology, the attempt to apply the rules of quantum mechanics to the universe itself, is still a young field. It is speculative, filled with competing theories and unresolved questions. But it points toward a profound shift in how we think about existence. Just as an electron exists in superposition before measurement, the universe might exist in a superposition of all possible initial conditions. There is no single Big Bang, but a haze of possible Big Bangs, each slightly different, each contributing to the wave function of the cosmos. These ideas are heavy. They are the extremes where our minds struggle to follow. Numbers too big, times too small, concepts too abstract. It is easy to feel lost, to feel overwhelmed. But notice how calm the universe remains. Notice how gently these ideas are presented. The foam of a bubble bath, the branches of a tree, the different stations on a radio. The metaphors are gentle. The universe is not chaotic. It is just very, very full. Breathe here. Let the cosmic scale wash over you without drowning you. The universe is vast, yes, but vastness is not the same as emptiness. The universe is full of structure, full of pattern, full of life and light and the quiet hum of existence. You are part of that fullness. Your breath is made of oxygen atoms forged in the cores of stars that died billions of years ago, stars that exploded in supernovae, scattering their elements across space. Your thoughts ride on electrical signals that obey quantum rules, electrons hopping between neurons according to probabilities. You are not separate from the cosmos. You are a way the universe experiences itself. The extremes are not meant to frighten you. They are meant to expand you, to show you that the reality you wake up to every morning, the sun rising, the coffee brewing, the clock ticking, is a thin slice of a much richer existence. You are not diminished by the vastness. You are part of it. Your consciousness, your choices, your breath, your love, your wondering, all of it is woven into the cosmic foam. You matter because you are matter, organized in such a way as to ask questions about itself. Reality branches quietly, without drama. Whether in the foam of the cosmos or the split of an atom, the mechanism is silent creation. There is no thunder when a universe is born. There is no applause when a quantum state decoheres. There is no fanfare when a galaxy forms. The universe simply unfolds, following its equations, exploring its possibilities, filling every niche with existence. It is generous, says yes to everything. Think about the word creation. Sounds active, loud, dramatic. We imagine a sculptor chiseling marble, or a painter splashing color onto canvas, or a god commanding, "Let there be light." But at the quantum level and at the cosmic level, creation is soft. It is the spontaneous emergence of structure from possibility. A particle appears not because someone made it, but because the wave function allows it. A universe inflates not because someone pushed it, but because the field settles into a high-energy state. Both are birthed not by effort, but by the mathematics of existence itself. The universe does not strain. It does not struggle. It simply is in all the ways it can be. Some physicists describe the multiverse as a landscape, a vast space of possible universes, each occupying a different point in the landscape. Some points represent universes like ours, with stars and galaxies and the potential for life. Others represent dead universes, empty universes, universes with bizarre physics where nothing interesting happens. The landscape is explored not by travel, but by creation. Each new bubble is a roll of the dice, landing on a different point in the landscape, exploring a different configuration of physical laws. We inhabit one point in that landscape. We see one configuration of the laws. But the landscape extends infinitely in all directions, and every point is equally real. Or rather, every point that is self-consistent, that allows for a stable universe, is realized somewhere, sometime in the eternal froth of inflation. The landscape is not empty. It is fully explored, every valley and peak populated by a bubble, a universe, a reality. Let us return to Earth for a moment. Ground yourself. You are lying in a bed. The room is quiet. The planet beneath you is spinning at 1,000 miles per hour at the equator. It is orbiting the sun at 67,000 miles per hour. The sun is orbiting the center of the Milky Way at 500,000 miles per hour. And the Milky Way is falling toward the Virgo cluster at 1,000,000 miles per hour. You are not still. You are in wild, dizzying motion, caught in a dance of gravity and momentum that spans light years. But you feel none of it. You are at rest in your reference frame, and that is the only frame that matters to you. Einstein taught us this: motion is relative. There is no absolute stillness. You are as entitled to consider yourself at rest as the sun or the galaxy or the cosmic microwave background. And that rest is real, even though you are moving at 1,000,000 miles per hour relative to distant clusters of galaxies. Similarly, you are in one universe, one branch, one bubble. Around you, undetected, unseen, might be infinite others, but they do not matter to your experience. They do not intrude. You are at rest in your reality, and that is enough. The multiverse, if it exists, does not demand your attention. It does not require your belief. It does not ask you to do anything differently. It simply is vast and indifferent and quietly magnificent. Imagine the foam again. Each bubble is a story. Each bubble has its own beginning, its own middle, and eventually its own end. Some bubbles last a fraction of a second before they pop. Some last trillions of years, slowly fading as their stars burn out and their black holes evaporate. Our bubble, our universe, is still young. There are trillions of years ahead. Stars will continue to shine. Galaxies will continue to dance their slow gravitational ballet. And perhaps, in some far future, the last star will dim, the last planet will freeze, the last black hole will evaporate into Hawking radiation, and our bubble will fade into cold, empty darkness. But by then, countless other bubbles will have formed. The foam is eternal. Inflation never fully stops. It continues in the vast, inflating regions, creating new bubbles, new universes, new stories. The multiverse is not just large. It is inexhaustible. It is an infinite wellspring of existence, pouring forth realities without end. Rest in this image. You are lying in a bed, in a room, on a planet, in a solar system, in a galaxy, in a bubble, in an infinite foam. You are nested, like a Russian doll, within layers of reality. Each layer is real. Each layer matters. And the deepest layer, the you that feels, that thinks, that listens to these words, that breathes in and out, that wonders, is no less important than the cosmic foam that surrounds it. You are small, but you are also infinite. You contain the universe in your awareness. The universe knows itself through you. The extremes teach us humility. They teach us that we do not know everything, that there are scales of reality far beyond our direct perception, that the cosmos is stranger and grander than we imagined. But they also teach us wonder. They teach us that reality is far more generous, far more creative than we dared to hope. The universe is not a stingy place, rationing existence to a single timeline, a single set of physical laws, a a single chance at being. It is abundant. It is overflowing. It says yes to every possibility. It explores every avenue, fills every niche. And in that abundance, there is room for you. There is room for your questions. There is room for your joy and your sorrow. There is room for your dreams. There is room for your sleep. The universe is vast, but it is also kind. It does not overwhelm. It does not crush. It holds you gently, even as it stretches toward infinity. Reality branches quietly, without drama. Now let the extremes recede. Let the Big Bang fade into the past. Let the bubbles drift into abstraction. Let the wave function of the universe settle into the background. You are here now in the dark. The universe has carried you this far. It will carry you through the night. Sleep is its own kind of cosmos, a private universe where the rules are different, where time loops and logic bends, where you can fly or breathe underwater or meet people long gone. Perhaps, in dreaming, you touch the other branches. Perhaps not. Either way, you are safe. You are held. The foam continues its eternal froth, but you can rest within your bubble, warm and quiet and at peace. When we speak of many worlds, the mind naturally jumps to the paradoxes. If there are infinite versions of you, why don't you feel them? If every choice is made, does any choice matter? Let us handle these thoughts with care. They are puzzles, not traps. Consider the paradox of identity. If the world splits when you make a decision, which one is the real you? The answer from the quantum perspective is soothing. They are all you. Think of your childhood self. The 5-year-old you is different from the you listening to this now. You have different memories, different cells, different thoughts. Yet you are the same person. You are a stream, not a stone. The branches of the multiverse are just more currents in the same river. Then there is the fear of chaos. Does a multiverse mean anything can happen? Not quite. The worlds that emerge must still obey the laws of physics. You will not suddenly float off the ground in a world where gravity fails, because gravity is built into the equation. The branches are variations on a theme, not total anarchy. There is structure in the infinite. Physicists also discuss quantum suicide or quantum immortality, a thought experiment where, perhaps, consciousness only follows the branch where you survive. It is a hypothesis and proven and controversial, but it speaks to our desire for continuity. The math suggests conservation. Information is never lost. Even if a branch fades from our view, it exists. Nothing is truly erased. There is a protection in this decoherence. We are protected from the noise of the infinite. We are evolved to focus on the singular, to hunt, to gather, to love, to sleep. Our brains are tuned to the frequency of one. The paradoxes exist in the math, but our experience is shielded. We are allowed to live a linear life in a nonlinear reality. Think of it as a form of cosmic politeness. The other worlds stay out of your way. They do not intrude on your breakfast. They do not shout over your conversations. They exist in silence, separated by the veil of probability. We are protected by the very thickness of the illusion, and that is a kindness. We have traveled far. We have seen the clock, the phone, the slits, and the bubbles. Now we stand at the edge, the frontier. This is where the map ends and the mist begins. This is the realm of we don't know. We do not know for certain if the many worlds interpretation is the correct one. It is a strong candidate. It fits the math beautifully, but we cannot call the other worlds to check. We cannot send a postcard to the branch where you became an astronaut. It remains an interpretation, a way of reading the map, not yet a proven destination. We do not know if the bubble multiverse is real. We have footprints, patterns in the cosmic background radiation that might be bruises from colliding universes, but they are faint. They are whispers that we are still learning to hear. Scientists are building better telescopes, more sensitive detectors, trying to catch the faintest echo of a neighbor universe. We are at the frontier of testing. Physicists are building larger quantum computers. These machines isolate particles in a multiverse-like state to perform calculations. If they work as predicted, they are harnessing the computational power of those shadow worlds. It is the closest we get to touching the other side. Standing here at the edge of knowledge brings a specific kind of peace. It is the peace of humility. We are small, but we are curious. We are limited, but our minds can span the infinite. The universe is still keeping secrets, and that is a beautiful thing. A mystery is a promise that there is always more to find. Recap: we accept that we are seeing a sliver of the whole. We accept that our certainty is a survival mechanism, not a complete truth. The universe is calm, even when it is strange. What feels fixed is often only familiar. As you lie here, drifting between the concepts of one world and many, consider where your own now is anchored. You are listening to this in a specific room, in a specific town, under a specific sky. There are thousands of others listening too, each in their own bubble of now, scattered across the time zones of this planet. We are a loose constellation of conscious minds, pondering the same mystery in the dark. We are connected by this frequency, by this shared curiosity. In a way, we are creating our own coherent branch of reality right now, a branch where people pause to wonder about the nature of existence before they sleep. If you feel a connection to this journey, to this quiet exploration of the big questions, you are welcome to stay with us. A simple subscription keeps this channel in your orbit, ready for the next night. And if you are still awake enough to move a finger, let us know in the comments simply where you are listening from tonight. Just the city or the state. It is a small way to map our own little universe, to prove that even in the vastness, we are here, together on this branch. Now let the theories fade. Let the bubbles pop and the branches dissolve into the soft background of your mind. Return to the room. Return to the dark behind your eyes. Listen for the clock again. Tick, tock, tick, tock. It sounds the same as it did before. The rhythm hasn't changed. The bed is still soft. The air is still cool. But perhaps the feeling is different. You know now that the tick is not a cage. It is just a beat in a much larger symphony. The single line of time is a story we tell ourselves so we can sleep. And it is a good story. It is safe to believe in the now. It is safe to rest in the certainty of this moment. The other worlds, if they exist, do not need you to worry about them. They are taking care of themselves. Your job in this world, in this branch, is simply to rest. You are exactly where you need to be. The universe is holding you in this specific probability, safe and sound. The vastness is not a weight. It is a blanket. Reality branches quietly, without drama, and tonight, your branch is drifting towards sleep. Let the questions drift away. Let the electrons spin in their clouds. Let the stars inflate in the deep distance. You are here. You are safe. You are part of the grand, quiet mystery. What feels fixed is often only familiar, and sleep is the most familiar friend of all. Good night.